This video is section 3.4, which is truth tables for the conditional and the biconditional. In section 3.3, we looked at truth tables for and, or, and negation. So we are continuing the truth table concept with the conditional and the biconditional. To help you understand the truth table, let's take a look at this little scenario here. In Normal, Illinois, there is a city ordinance designed to aid city street crews in removing snow. And the ordinance states that if there is snowfall of 2 or more inches, then cars may not be parked overnight on city streets. So here's our P. It snows more than 2 inches. Q is no parking allowed on city streets. I just abbreviated here. So under what circumstances has the ordinance been violated? So if it snowed, then nobody's allowed to park. So if it snowed and no one parks, is that a violation? No, that is not a violation. If it snowed and then people parked on the streets, is that a violation? Yes. How about if there's no snow, people parked? Well, if there's no snow, people can do what they want. If there's no snow, then parking is allowed. Is that a violation? No. If there's no snow and nobody parked, is that a violation? No. So the only violation we have is if it snows and people parked. So if it snows is my P, then people parked, they were not allowed to park. If they parked, that is not Q. So that's what gives me this truth table for the conditional. Notice, the only time the conditional is false is if the premise is true and the conclusion is false. The premise is true and the conclusion is false. That was our scenario right here. It snowed and people parked even though they weren't allowed to. That was a violation, and that's when we get a false in the conditional truth table. So the definition of the conditional, a conditional is false only when the antecedent, that's the P, is true and the consequent, that's the Q, is false. So that's the only time we get a false for the conditional. I need to clarify something about this antecedent and consequent. In this particular case, P is the antecedent because it's first. Q is the consequent because it's second. You could see one later on that has R, Q. That means R is the antecedent and Q is the consequent. I could have Q, R this way. This means Q is the antecedent and R is the consequent. So P is not always the antecedent. Q is not always the consequent. It depends on what letters are being used and in what order you see the statement. So let's take a look at some truth tables using this conditional. Remember, the conditional is just one single arrow. Now we need to build this truth table. We need to have a column for not Q. We will need to have a column for not P. And then we can have our final column, which is not Q, not P. So not Q is just a matter of negating the Q column. The Q column is right here. Negate means change those around. So the truth values have been flip-flopped. Same thing for not P. I will flip-flop these. So this goes to false, false, true, true. So right next to each other, I have the not Q, the not P, and I need to do the conditional for not Q, not P. Remember, the only time the conditional is false is if the premise is true and the conclusion is false, and that is right here. That will be false. Otherwise, we have trues. The truth value of a conditional statement does not change if the antecedent and consequent are reversed and both are negated, which is what we did in this one over here. Notice on the other screen, we had if P then Q. Now this one, put the Q in the front, the P in the back, and I negated both of them. That's exactly what I just did. This truth table, this concluding column, is identical to this concluding column. What that's telling me is that if P then Q is equivalent to not Q then not P. And the symbol for equivalent is 3 lines for an equal sign. So you might be asked to write the equivalent statement in words. If I live in Port St. Lucie, then I live in Florida. To do this equivalent statement, what this tells me is that I can take this part, the I live in Florida, and it goes in the front, but there's going to have to be not somewhere in the statement. Then I'm going to take the I live in Port St. Lucie. It goes to the back side, and it also will have to have not somewhere in the statement. And what that looks like is this. If I don't live in Florida, that was this part going to the back side with the negation. If I don't live in Florida, then the Port St. Lucie part goes to the back, then I don't live in PSL. We have seen the biconditional statement before. This is P if and only if Q. Really gets broken down into two parts, if P then Q and if Q then P. So symbolically it's this. Then let's do the truth table for this and see if we can figure out what the final truth table would be for the biconditional. Of course we know the P must alternate T, T, F, F. The Q is T, F, T, F. Now we just looked at the conditional if P then Q. The only time if P then Q is false is if the premise is true and the conclusion is false. So this is false, but the rest of these in the column are true. Now this is going the other way around. This is if Q then P. So now this column is considered my premise. The only time the conditional is false is if the premise is true and the conclusion is false, which is this right here. So this position over here gets a false. The rest of these will be true. Now I need to put these two columns together using the connective and. True and true is true. False and true is false. True and false is false. True and true is true. Remember, another way to look at and is the only time an and statement is true is if both are true. True, true gives me a true. True, true gives me a true. What I have just done right here is to show you what the final column is for the biconditional by breaking this into its two components, which is what this definition says right here. A biconditional is true only when the component statements have the same truth value. See where we got our T's? The only way to get a T for the biconditional is if they both are true or they both are false. So a biconditional statement is true only when the component statements have the same truth value, meaning they both have to be true or both have to be false. Now, what we're going to do right here before we continue with the conditional and biconditional examples is just look at all of the truth tables we have done in section 3.3 and 3.4 just so that you have straight in your head what they look like. This is a negation of P. The only thing we need for this is P, and with one letter all we have is true, false. And if we have the negation of P, we just change the true to false, change the false to true. That's all there is to negation. Now, P and Q, do you remember? The important thing about and is the only time an and statement is true is if both components are true. This is the only place we have both being true, therefore this is true, and the rest of these must be false. For P or Q, what do you remember about or? The only time an or statement is false is if both components are false, which is right here. This must be false. I've also said to you several times that another way to look at or is if you have at least one T, this one happens to have two T's, then it will be true. All right, we just learned the conditional truth table. If P, then Q. The only time the conditional is false is this right here. Premise is true, conclusion is false. The rest of these are true. And a couple screens ago, we did the biconditional, and the way the biconditional is true is if both truth values are the same, both true or both false. And this in here is false. Now, the reason I did this is to lead to this. This is a nice little chart that you could put on your index card because it shows you all the basic connectives, or, and, conditional, biconditional, all together in one little chart that would be easy to put on your index card. The only thing not in the chart is the negation, and that's okay. That's pretty easy to do in your head. We're going to look at two more definitions before we end this video. There's something called a tautology, and that's a statement that is always true. It's also called an implication. Now, what tautology means is that whatever your last column is, you will have all T's. If your last column has all T's, then you are dealing with a tautology. So this says, show with the truth table that if P, then P or Q is a tautology. So I have to build this. We already have our PQ right here. We have P. I don't need to rewrite that, but I do need a column for P or Q. And then my last column will be P, then P or Q. So we know with the connective OR that the only time OR is false is if both component statements are false. So this one's false and the rest of these are true. Then I need to look at this statement, if P then this column, if P then this column. The only time we have a false for the conditional is if the premise is true and the conclusion is false. Do we have any of those? Premise is true, conclusion true. Premise true, conclusion true. Premise false, conclusion true. Premise false, conclusion false. We do not have anywhere between this column and this column the situation where the premise is true and the conclusion is false. Therefore, all of these are true, and that means this statement is a tautology because all of the last column is true. Another thing that you guys can do that I can't really show on this screen here is that we didn't need this Q part right now when I was looking at these two columns. So you guys could take a piece of paper or a pencil or your thumb or whatever and just cover this up. I'm done with that column. You might get that out of your field of vision so that you're only looking at those two columns. There is something called a self-contradiction, and that's a statement that is never true. That means the last column would have all falses in it. So this says, show with the truth table that P and not P is a self-contradiction. So of course I need P, and we know P is true, false. Not P has to flip-flop this. This goes to false, this goes to true. And then let's put these two together, P and not P, together under the connective and. Well, true and false would have to be false. False and true would have to be false. And that is a self-contradiction because my entire last column is false. Now that one makes pretty much sense that that's a self-contradiction. A statement cannot be true and false at the same time.